So welcome to our 9th lecture on AI. So in our previous lecture, we learned about the existence of first-order logic, or at least you had a review of first-order logic. But the question is, now we have we have a nice way of creating these relations, of creating these objects, basically this, of recording facts about the world, basically, right? But inevitably, we will be not only storing facts in our database, in our knowledge base, but we will be want to ask questions, right? So, and we will update information probably. That also seems pretty easy, but how do we, if we ask a question which is not in a database, in a knowledge base, right? How do we draw inference, right? How do we create a new sentence? How do we verify, is this sentence true or not, right? So we'll look at some algorithms, some ideas, how this is actually done under the hood, so to say, right? The ideas. So let me open the notebook again. Let me open the code space on our GitHub. Well, let's start this notebook. So one of the ideas while we're spinning this up is to use our propositional logic. Right? We can do actually quite a bit of converting from regular. If we have a universal quantifier, right? We can convert that to basically. It's just handy. It's not really needed, really. Because, well, let's take a look actually, right? Let's take a look at this. Maybe I'll draw an example of what I'm talking about, right? So propositional logic, which was simpler but much wordier, right? So, so we look at three main ideas: forward chaining, backward chaining, and the resolution-based theorem proving. So. The big first idea today is something called universal instantiation. So what does it mean, really? That means, let me again do this something like in a paint, right? And if I do, right, so I will do our greedy king again. Well, where's my pen? There's my pen. Where is my pen? Where is it? Oh, there it is. All right. So we have a universal. This first-order logic, so, right, all x, right, all x, king x, right, king x, right, and greedy x, right, follows that it is evil x, right, x, 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 right? So, this is first-order logic. So what we can do this, we can simply get rid of this universal quantifier, basically just plug in x, right? Because it will work for any. So you can go to King Charles, right? So you can say if King Charles is, right, Charles, and if it happens on greedy Charles, right? Greedy Charles, I really need it. Only if there's some sort of pen which makes change colors instantly, right? Have you seen that YouTube video where this guy does math, but he has used like 6 pencils in his hand, like he draws formulas and he just keeps changing colors, right? I would like to do that. Or I need some like color picker or something, right? Maybe you can come up with some controller for this, some idea. If you come up with a controller, let me know, right? Like there should be some way, some way of quickly, like shortcut for this basically, right? I don't want to, I'm too lazy to click there. I want to click here or something. Any ideas? No? Yeah, so basically, yeah, of course. Maybe there should be some voice control, but no. But now they have pens with different boards which have different controls, like so you can assign a hotkey. But okay, that's beside the point. So we can now, of course, evil, not Charles, but evil, right? All right, now one more. So evil Charles, right? Evil Charles, right? And of course, same applies to King John and so on, right? And King John, and I'm lazy, and so on, King to, I don't know, King, who else? King James, right? King James, right, of course, right? Right, so, and so on, right? Right. So, talking of course LeBron, of course, right? So, but yeah. this is all, so we can convert this. So we can, oops, okay, that works. Right, we can convert this. So universal instantiation, universal, I think, universal instantiation, right? I can't spell, but yeah, you get the idea, right? So that's the first idea we can do, right? That's only for universal quantifiers. So we get rid of universal quantifiers, right? So 1 second, let me see here, right? Right. So we converted that. So can we convert everything? So the question, of course, is we just plug it in, right, and we check basically the orders, right? So now let's look at something we can do with some. Let me see my examples, right? So extension station, right? So we find the unique extensionally quantified variables, right? And basically we state them again with concrete statements, right? Okay, so how does that work? That works as long as this constant has not been used in a knowledge base. Right? So you need a new knowledge base, you need a new variable basically, right? So we can create these, so we can basically, technically, we can transform our first order knowledge base to a propositional knowledge base. All right, so let's look at actually, right, something in real life, not real life, but see some examples. All right, let me see if I can show you some good examples. So, but that's not all, right? Right. Let me see. We saw the three bound variables before, right? So let's look at all right. So this will be example. Let's do another paint job. Right. So again, we'll go back to kings, sword, and who owns what, right? So King Arthur, right? Back to the wall. King Arthur, right? Right? Sword is Excalibur, right? Excalibur, right? Round kings and a knight on the round table, right? Sword, okay? Now I need to figure out the propositional statement of this. King Arthur, sword. Okay, oh yeah, he owns, right? So who owns what? Owns, right? That's a relation, right? So probably I would say Arthur first, right? I'm doing this from memory, but it makes sense. Arthur on Excalibur, right? Excalibur. And so those are facts, right? King, sword, Arthur, right? Now we need to have a sort of rule. We need to come up with a rule. So if someone is a king, so all kings, right, let's say any king, right? All kings, right, and they own a sword, right? This is true for all of them. As long as they own a sword, right, they are going to be a warrior, or big warrior, or great warrior. Let's do this. So let's do this. Quantify this rule, right? Facts. These are facts. Rule. So all x, all y, right? And now we do, of course, this simple thing: king x, right, and sword y, and owns, who owns what? Owns x, owns y, right? Owns x, owns y, all right? And why is this rule there? I should probably do another parenthesis. So I guess I don't know if it's completely correct formally, but I will. So it follows, right? It follows that they are, x is a warrior. Warrior x, right? So king, if you are a king, and if you own a sword, right, then basically you are a warrior. Warrior king, but let's call him warrior, basically, right? So, now we have a fact. Is Arthur a warrior? That's the question. Is Arthur a warrior?
If we follow this rule?
Yeah. Yeah, of course. I mean, it's like duh, right? But yeah, but it seems obvious, right? But and we'll see that it's actually the yeah. So one of the ways of doing inference, right? What you do is you just plug in values, right? Seems simple. In this case, it's extremely simple, right? In this case, we just plug it in. That's so this is oops again. So this is going to be our approach. We are just going to plug in the values, right? Right? So we are asking, right? So ask, right? So ask EB, right? Ask knowledge base, right? Warrior Arthur, right? That's a question we want to ask. That's like a function call, basically, right? That's our knowledge base, right? Because this fact is not it's like it's always on tip of our tongues that it's yeah, it has to be a warrior, right? But proving it actually is, you still have to follow the process, right? Trust the process, so to say, right? So, right. So let me do the forward chaining. Let me see if we can find an example for this actually. I have an example somewhere here. So basically we just plug, so we find matching rule. We have Arthur, we need to find X. All right, so basically find Arthur, right? Arthur, right? Okay. And we have basically then Excalibur, right? We find that fact, right? And it matches. So we find, okay, so Arthur is X, right? X is Arthur, right? And Y, of course, then is going to be the Excalibur, right? Right? And of course, that automatically plugs in true, 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 true. So true, 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 when you plug it in, right? And obviously all three are true, then it follows that X is warrior, right? So forward chaining, right? Extremely simple, but you just plug it in, right? So the question is, what's a big problem with this approach? Can you imagine why is this forward chaining not so great, I would say?
So we rely only on the truth value.
Well, here's the problem. I'll give you. Yeah.
We have to check always.
You have to. Okay. The problem is this. Let's imagine you have like 500 rules, right? And you have like facts, like 1,000 facts, right? Then you have an issue of how do you plug it in, right? Brute force approach. Plugging in, right? You're going to get, I think you'll get, like with a naive algorithm, you'll get brute force will be like exponential, actually, right? Checking everything against everything, right? So it will become computationally infeasible. Basically, you can't do it really in real time, right? And that actually is the issue. In theory, right? Order logic, we can create something as difficult that you cannot actually solve it, as you remember from your prologue programs, right? No matter how fancy an algorithm is, you can end up with such a messed up knowledge base that you cannot get useful facts, or you don't get all the facts. However, what's going to happen with this is going to generate a whole bunch of facts, right? You're going to plug in and just keep getting facts, right? Maybe there's King James, right? Well, he doesn't know Excalibur, right? So he's, the fact does not exist, right? He owns something else, right? So eventually you get a whole bunch of facts, right? Some will be true, some false, right? Because who says, for example, in this case, you put them reversed. Arthur is the sword, right? And Excalibur is the king, but it's false, false, false. Obviously, all three are false. And of course, it all breaks down. I mean, you could optimize a little bit by say, okay, if first one is false, right, then we don't need to check the rest, right? The old trick of optimization. But still, right? Still, this is just not very good if you need to have a specific fact. So that leads us to a second approach. What kind of, okay, you want to find out whether King Arthur is a warrior. What's the other approach? What do you think? Like, yeah. So, I mean, like we started from the beginning. We can sort of go the other way. So backwards, right? Because we only need one specific fact. So we can start with what we are trying to prove, this fact, right? So just imagine here, let's imagine we have a whole bunch of facts, right? But if we plug in Arthur here, we want to get this first, right? Then sort of things will start to fall into places. We will be able to all those King James, King John, all those facts, all other swords, right? We can ignore because this will pick up, we'll have a linear sweep, right? We gain a lot of linear capabilities. So if you have a specific fact here, backward chaining makes much more sense, right? Because we sort of, oh yeah, X, I mean, Arthur, right? Okay, all right, so we can start with that immediately. That makes sense. That makes a lot of sense, right? So we can go backwards. We'll look at this example in a little bit more detail in a moment, right? So that is a big improvement, basically, right? Yeah. So, with forward chaining, again, you could supply like an array terminator, basically. Right? If you find this particular fact, then you should stop. But again, there's no guarantee it will stop immediately. Maybe it'll give you a bunch of useless facts first, right? Which you didn't ask for. So again, backward chaining, which I already mentioned to you, is, I think, better algorithm underneath. Right, so let me see if I can find the backwards chaining idea. Backward chaining, right. So, let's look at the king. Say forward chaining. Forward chaining. Welcome back. So we will have actually, let me see, do we have let me load this up again. So, let me see if let me open it up again, because I'm too lazy to do it again, right? So forward chaining. Let me just clean some facts. So the ask stays the same, but instead here, right? So I'm going to clean this, right? I'm bigger. Just single size. Come on. Is that where? This one? This one? Oh yeah. This one. Yeah?
Yes.
It's larger.
Can I get something bigger?
No.
No? Oh, come on. What kind of?
But you can select and then.
Yeah. All right. I'm playing Control X. Right? Yeah. All right. That works. Yeah. That works. All right. Now. So backward chaining is we start with this, right? So then warrior X, right? Warrior X, we start with this fact basically. Warrior Arthur, right? Right. And then, okay, we have Arthur. There we go, right? So all the other kings fall away automatically, and all this, princes and princesses and all whatever, right? All the other facts automatically will fall away, right? So, again, maybe we'll have some other facts, but we have, of course, it still doesn't solve all the problems, right? We have maybe King Arthur is also a tennis player, I don't know, right? So, you'll have to consider that fact as well, right? But at least you have King Arthur, and we see, okay, it's here, right? There we go. So Arthur goes here, and automatically we can sweep. Okay, do we have anything else interesting? Oh, we have Owen's, and we have Arthur, we can plug it in. All right, and then we get Excalibur, right? We get to King, right? Then we sweep linearly here, we find Arthur, and we can find, okay, we have so Y should be, so we start, so X, so from X, so X is Arthur, right? And then also owns for Excalibur, right?
That means that the only thing kind of omitting is the evaluation process.
Yeah,
They'll still have to traverse all of them to understand it.
yeah, I mean, like I said, it's better process than just going forward, right? Because we can see, so we can find the relevant facts, right? But we still potentially might have multiple, right, of these, right? It might still not be resolvable, right? Because let's say, okay, if I want to find again something about, I don't know, princess, of course, then we don't find it. There's no prince, there's no fact of prince. It just doesn't work at all, right? But in this case, it's, how we can see that starting from the, checking whether it's true, starting from this is easier, actually, right? Because sort of it suggests, okay, we can plug in, because we know this is what we want to find, right? So, maybe, let's see if there's any step I missed. Maybe this is, yeah, we prove King Arthur, we prove sword is Excalibur, right? And that's it. We find all three. So basically, like, we find all three true, and so Y equals Excalibur, right? And again, we have solved it, and it goes automatically. Now, our promise is proven, so naturally it's all by modus ponens, yeah, it is proven, yeah, so. And again, in this case, the main difference with forward chaining, we gain a lot of solutions, basically, possibly, right? With backward chaining, right, as soon as we will prove one specific thing, right? So, so forward chaining is actually used more in like sort of like more expert systems. Backward chaining is used like in theorem proving a theorem like this. You can prove a theorem, specific theorem, right? If you set up facts, it just follows through, and there you go. Now, but again, the issue with all these, why didn't we solve AI with this first order logic? What do you see? The issue is even with this backward chaining, we still, on a large knowledge base, we still cannot show all the facts, right? We will still run into problems. Let's see what the book says about it, actually. I've forgotten what it says, right? So storage, right? We can do all kinds of tricks, right? Things you are now indexing, caching, like some previous solutions, things like that. We learn an algorithms course, of course, for efficiency, but still does not solve all the problems, right? So, forward chaining, right? We focus on definite clauses, right? Right. It's very, very powerful. So, right, and the thing is, there was a story of data log, right? This is like the first, I would say, expert system. Let me give you an example, data log. Data log expert system. Yeah. Let me see if it's still around. Right. Expert system, right? Symbolics. This is, of course, all early code is all written in Lisp, right? Right. So let me see, what is it called? Before prologue, after data log. Let me show you what data log looks like. It's data log. Let me show you. It's kind of like prologue, but it's not quite, right? It's not like prologue, right? So let me see if I can make this bigger to you guys, right? Okay, right. It looks kind of like it's synthetically a cellular prologue, right? So the difference is bottom up, right? So synthetically, it looks very much like prologue. So those who are taking programming languages, me, we'll see Prolog soon enough. And some of you already have seen Prolog, right? So, but the difference here is actually backward chaining, basically, right? So that's a difference, a pretty crucial difference. So the question is now, actually, where can you see datalog in action, right? So you put facts, you put rules, right? Facts and rules, and then you can ask questions, basically, right? Yeah. So instead of answer queries, you ask for something, right? You get Brook and Damocles, right? Brooks and Damocles, right? So if you think about, okay, yeah, who uses datalog these days? Probably not many people, but there is actually a relation to SQL, right? Structured query language, which also has to do something like this, actually, if you think about it, right? It has to do some sort of queries, right, to retrieve knowledge, right? So something, right, when you write this general query, select something from something, right? How does that do? How does the database actually go through and process this, right? For database engine, right? So let me see here if we can find an online tester, right? Right. So it's been used for bottom up, right? Yeah. Right. And let me see. Oh wow, look at this nice super engine. There's actually parallel. There's a parallel implementation, right? So I want to see if I can show complexity, right? So basically, right, that was actually not Turing complete. That's very interesting, actually. It's not a Turing complete language, actually. Kind of interesting. But of course, there's extensions which make it Turing complete. Can we play around with it? Right. Yeah. Right. So the big difference with Prolog is that in datalog you can make your facts, right, your statements in any order. You remember from Prolog, you had to have specific order, or you mess things up and then you hate your life, right? So, so in that regard, maybe datalog might be a better language, but of course it's completely, who is using datalog now? Okay, actually there's a couple things, right? There are some things using it, right? Relatively few, relatively so one. Of course, some worked in Rust, I don't know why they did it, right? Let me see the years. Right, Klingo, C-Lingo, Data Hike. Closure, of course in Closure, right? So there's like 5 or 6 different Closure versions of datalog, right? Again, you might be asking, why Closure? Because of course Closure makes it very easy to make custom languages, basically, right? It's because there's so few constructions in Closure. You make up your own language, basically, right? So very well suited for this. Of course, Java, Go, C++, and so on. Okay, but that's again something if you are interested in this in datalog on creating an expert system. But what I wanted to ask you, not ask you, but show you is the expert system that the book mentions. Actually, it was used for shopping, basically, for buying very expensive computers. It was early expert system, but yeah, all right, so that's the algorithm, unify, right, on matching rules against facts, right, so, no. Yeah, so I mentioned irrelevant facts. The book mentions that that's a big problem, right, so huge computational waste. So backward chaining is the solution, goal-directed approach. So, you check, right, all clauses, right, that could unify with the goal, right? Now, let me see if I can find the third method. We'll get to that today. Hopefully, right? There's one more other thing, actually, right? This is a potential problem with backward chaining. I didn't mention this. Let me start a new one. Where we have new, right? Let me do new. Let's do a new file. New. Yeah. Let's not save it. But the problem is this potential problem. Right. So ancestor xy. So let's do this. This is a rule. This is a potential problem. We have ancestor, let's say xy, right? Ancestor xy, xz. Yeah. Oh, what does that sound? Something's rebooting? Or what is it? Ancestor xz on the parent. Okay, so this is kind of example. The parent yz. Let's see. It should be reversed actually. Okay, so okay, here's the issue. Basically, if your rule consists of two facts, functions right here, right, functions which have recursion, right? Basically, you will get infinite loop, right? So it's the backward chaining. Basically, you won't be able to solve this basically because you'll keep inputting when searching for something. You'll keep inputting the ancestor. So maybe this is, I don't like this example from the book. I want something simpler, maybe, right? So if parent leads back to the ancestor, right, AB, right? So it will never terminate. So of course what you can do, of course you can check, have I been looping? Have I been thinking about myself? And like have I been meta thinking? It's kind of like this. You can sort of implement loop detection, right? Or limit recursion depth, basically, right? So also, of course, I mean this is kind of obvious, but if you have chaining, is going to fail if you don't have missing some fact, right? If you don't have that sword rule, right? If you have something missing, right? It goes without saying, right? But if one of these facts is missing, again, you remember from a problem, you forgot one fact or maybe messed up, it's gonna, it's not gonna find it basically, right? All right. Now, what else do you want to see here? And so backward chaining algorithm, right? So backward chaining is quite often used. I think Prolog might also use this again. So, right, so there's another example, criminal, right, what was this example? So if criminal sells, this is a book head. If you sell, let me see the example. If you sell missiles, if you sell missiles to the enemy or something like that. Yeah. Okay, the law says it's crime for an American to sell weapons to hostile nations, okay? Right, and if sell country, no more is the enemy of America, probably Canada, right? Canada is an enemy of America, right? And you sell weapons, right? And your name is Colonel West, right? And you're American, right? So you become a criminal, right? So, yeah. So owns, right? So same thing, right? Owns missiles, right? Owns, right? So, but this will be a little bit harder. Let me think about this, right? So American. Let's do this one more time. So let's do one more. So we'll do these facts. So this will be the rule. American weapon sells. Yeah, so American, or let me make this bigger. American X, right? On weapon Y. Weapon Y. Enemy, of course, will be Z. Enemy will be Z, right? On, of course, sells. So sells who? This is a three-way relation. So X, Y to Z, right? And of course, it means you are criminal. You mean this guy here, or girl, right? Criminal X, right? So then you have, I think the book says, so American American will be, we'll call him West, right? We can suggest different name, let's call him West, right? And then weapon, I don't know what we call weapon. But they, you heard about that, there's a law in America now, they want to prevent DeepSeek from like in a, to make it illegal to use DeepSeek in America. Yeah, but it's not a law, I mean, it doesn't affect us, right? And they will be losers, not us, right? So, I don't know, Patriot missiles or something, right? Patriot, right? Right, Patriot, right? Enemy, of course, will be Canada, right? Right. So, and of course, is Mr. Colonel West, is he a criminal? Is he or not? If you have these facts and this rule. So, is he a criminal or not? Or is this answerable? Think about it. Enemy Canada, weapon. I hope yes. Then we're missing a fact. We're missing what? We're missing the fact. I mean, yeah, I'm an American. There's Patriot missiles. There's enemy Canada. So what? There's no fact of selling, right? So you need that. So if you sell, sales, I don't know, West, Patriot, sells to Cuba, right? I'll probably get now YouTube algorithm will probably cancel me, right? Yeah, Cuba is one of those trigger words, right? Canada probably is going to be a trigger word too. But okay, so, but of course now, well, is he a criminal? Not by these rules, right? Because enemy Canada, right? Not Cuba at the moment, right? So obviously, right? Obviously, yeah, this, and now of course we just need to West, Patriot, right? And of course Canada. And now, yes, now we can prove it, yeah, indeed, he's a criminal. And of course, again, if we are going to do forward chaining, we'll keep adding these moving around, it will be a big mess, right? If you go backward, it will be easier, right? We have criminal X, right? So what could be X, right? Well, we can plug in, right? So we plug in, we need something matches, XX, right? So we need something that's American. We only have an American here, West, right? I mean, you have American East, right? American Ronald or something, right? Right. Not talking about old Ronald, not talking about, of course, Ronald Reagan, for example, right? So, but yeah, so obviously now, okay, you have two potential X's, right? Again, right? So not only one X, you have two. Okay, now of course, if we so happen to use West, and then it's easy. Then we need, okay, somebody's weapon. Oh yeah, there's Patriot, right? And then there's enemy Canada, or no other definitions, right? So then we have, here's a fact, right? And okay, it all nicely plugs in. And again, it can be proven basically, I don't know if it's linear time or quadratic. I still say it's quadratic because you have some, again, here it's hard to say the complexity. Right? It's beyond the scope of this lecture to talk about the complexity of this algorithm, right? But again, there might be, again, the more facts, there's going to be, I think, still linear quadratic complexity at least, right? One of the issues is that with these systems, these factorial systems, these logical systems, there is an overhead. There's overhead of about, I think, log n on top of regular programs. So it's not really good for general computing, unfortunately, right, these systems, right? They're good for proving certain things with certain optimizations, basically, right? But we can't just do it for everything. Now, let me see if I have anything else. We have one more. Oh, come on, let's start code space. All right, so we can, again, irrelevant fact, so backward chaining. Backward chaining is awesome, right? As far as, best, no. Right. So, one more thing is how to do a negation. And that is kind of interesting, right? Let me see if it's loading up. Yeah, I know it's pre-unification. Do we have the backward chasing? Did they mention this here? Resolution, right? Yeah. Right. This is who this guy, Tos column, right? Yeah. So if you can convert them to conjunctive normal form, right? This is the hardest one. This is the one I would have trouble. Well, I wouldn't do this by myself. I mean, or let an engine do it myself. Do it instead of me, right? I wouldn't want to do it. But let me show you the third approach. There's. Let me see if you can find it. Backward forwards chaining. Okay, so the resolution proof is kind of weird actually, right? So let's go back to our, do we have our sword example? That's American. Let me load again this. Forward chaining, no. Okay, yeah. So back to this one, right? So this we saw forward or backward, right? But now we can do, basically we have to convert this. And this is, I don't know, you covered De Morgan's laws. Did you cover De Morgan's laws? Yeah, you did. Did you have to do some work with them, right? Yeah, you just convert. So, okay, so I will not go into details, but you basically go through, and you have this, you can change this basically. This fact here, I'm going to delete this a little bit and maybe cut this here, because this is all, don't need this anymore. Control X, right? Let's clear. So, after De Morgan, right? Let's see what do we get. Let's see, I don't know if anybody remembers exactly, but it should be in conjunctive normal form, or let me see, for all x or y. Let me see, we can do this here. Not king. If you, or this, that's disjunctive. Let me see, can we make this? Okay, so basically, how could we rewrite this? Let me see this. Let me see this through. So not De Morgan's laws. De Morgan's laws, right? Conversion, right? Conversion. So basically, you get this: not king x, right? Or not sword x, I believe, yeah? Or not, does not own xy, right? Or not a warrior, right? Or not a warrior. I'm not, and you will have to, maybe you can find if I'm, this looks broadly correct, right? So either the question is maybe too old, but I think this is correct. So not a king, so either there's not a king, or either it's not a sword, or either x does not a sword, right? Or either warrior is not x, basically, right? So this certainly looks a good, certainly true statement. I mean, if you apply this rule, basically. The question, of course, does it cover all the cases, right? If it's a sword, then, right, so this is certainly true, but it's universal. I think it's universal. Yeah, it's universal, yeah. Okay, so that's the first step. So you convert it, right? And there are going to arguments for that. And then what you do is, right? Yeah. Then you do add it to the knowledge base. You add, what you do, this good old process of proof by contradiction or proof by negation in this case. We add the fact that this is not not varchar, basically. We add this fact to the database, basically, right? I believe we add this fact to database. Oh no, right? Like a negative fact, right? It's added to these facts. And then let's see what happens. So what's gonna happen, of course, we can plug it in until it will cancel, everything will cancel out, right? Let me see if this is correct now. The approach, right? We had this fact, right? And right, so basically the resolution process will find the king Arthur cancels with not the king Arthur, basically, right? So this process will basically cancel all three of them out, right? All three, these will cancel out, right? Will cancel out, right? Will cancel, right? And I think if I do it correctly, right? Right. Oh, no, this is okay. So you see, there's an issue. This is a part here, right? So this has to be all varchar. So okay, yeah. So that's the correct way. This is, you see, this one negation completely ruined everything. So it has to be so either it's varchar, right, or not a king, not a sword, or varchar, right? Yeah. If he's not a king, right, it's not a varchar. So he's either varchar or one of these is true, right? That makes sense now. That's much more sensible. Yeah. Okay. So okay. Now we're cooking. Okay. So now all these will cancel out. Yes. Are we cooking? Not so much. Right. So now we will get to the fact that basically the issue is this. So now if we at the end of the day do this, which also cancels out, right? We end up with what? An empty set, nothing, right? And that's contradiction. So one of those have to be true, right? Right. So this means you create a contradiction, and as you remember from proof by contradiction, right? So the other part, so that means King Arthur has to be a varchar, right? And again, this was a simple example again, because of course the process of converting to this type of form is also not trivial, right, in expensive cases. And again, you still are left with the fact you need to find, okay, what do you plug in, right? Plug in, right? And I wonder again if it's possible if you don't find that if something doesn't cancel out, well, obviously you're left with not a, you can't prove anything then, right? So negating the query, add database, do the resolution, and then hopefully find the contradiction, right? You have to find something. So, right, conjunctive normal form. Let's see. So this is, again, so this last one is it's hard to follow, I think, if unless you are one of those rare persons who do like the Morgan in your sleep or something, right? So, yeah. So, but luckily, of course, this is all also the algorithms for converting, right? So that's the good news for you, right? Now, right, so criminal west. Yeah, we could do this. Yeah. And of course, now we get to the last part is, of course, Kurt Gödel, right? Kurt Gödel. You've heard of him, right? And his incompleteness theorem, right? Right. Yeah. So he was a big, what happened, of course, let's go a little bit history. This factorial logics appeared in late 19th century, right? And there was this idea you could make up these rules, everything, right? And then you could sort of complete your math. Everything would be there, full, right? Decidable, right? And complete, right? And there's some really good mathematicians who are working on this, right? And then Kurt Gödel in 1930s, right? He proved that actually, if you have a sufficiently powerful formal system like this, right? There's things you can either not decide, right? Or it might not be complete. You cannot have both, basically, right? So that's he says. So basically, there exist some things that you cannot prove, right, within the system, right? So you cannot have both, right? So the real this formalism, this formal languages have some real limits. Again, those limits in real life might not be so apparent, but it leads to. But Turing and Alonzo Church in mid-30s, right? They already knew this Gödel's result was known already. So they basically show that there's things you cannot decide, these computable systems. So famous halting theorem as well, right? You had a halting, right, theorem, right? You talked about halting theorem anywhere? You talked halting problem, right? So you have a computer problem, right? You discussed this, right? So there's no algorithm to solve this, right? Yeah. So this shows that you can define some things which you cannot compute, basically, right? In general, right? Yeah. So basically, you can make this means, of course, how do you prove these type of things? You prove it by recursion, right? Basically, you sort of show, you can build a program which tries to prove itself, basically, and there's going to be a problem. It's sort of like a variation if, let's see, the barber, who shaves the barber problem? Let's see, who shaves the barber, right? Right? Barber paradox, right? Barber shaves those who do not shave themselves, right? Right? Yeah. Does barber shave himself, right? So, barber cannot shave himself, as he shaves only those who do not shave themselves, right? Because if he shaves himself, he cannot be a barber anymore, right? But, however, if he does not shave himself, then he will be one of the people who should be shaved, right? So he must shave himself, and so it goes back and forth, right? If you determine like this, it's a loaded question, basically, right? So there's also, of course, liar's paradox, right? Let's see, where's you see first order logic appears here, right? Right? There exists a person, right? And all persons, right? Y shaves xy equivalent to not shaves xy y, right? So it's not satisfiable. Basically, there's contradiction, right? So this is one of the problems, basically, right? So so there's no solution to this problem, basically, right? Big problem. I want to go back to, what was it? Cretans, all Cretans are liars. All Cretans are liars, right? This goes back like 3,000 years ago. Epimenides paradox, right? Right. A genius. Epimenides, he was from Crete, and he said, all Cretans are liars. So what does it mean? Right? Did he lie or not? Did he tell the truth? Right? So how would you solve this, right? I can't spell, I don't speak Latin, unfortunately, not very well. Promptuari econum insignorum. So, of course, all this comes because of recursion. As soon as you have recursion, all the stuff happens like this, right? So, was he liar or not?
That's a question.
Yeah. It's a philosophical question, right? It's basically, of course, it's undecidable. You can't really answer it. The answer, I believe it's in this book also, you have to say mu. It's like you can't say, it's like a now, mu is like not like a cow, but like a Buddhist monk or something, right? You're basically one of those things you can't answer. Like it's a question you can't really answer, right? So, yeah. So if he's a liar, right? Then he must be telling the truth. This is not that all Cretans are, But I think this one you can solve, right? I think this one is still not a complete paradox, is it? Because he said all Cretans are liars, right? So if he says all Cretans are liars, then he must be he's lying, right? Mm-hmm. Right? But the question is, all Cretans are liars. The opposite is not no Cretans are liars. Maybe some Cretans are liars. So that's the thing. I think this thing can solve it, sort of, right? Yeah. You see? Yeah, at least. So because you see, this is not a completely because at least there's at least one Cretan who is honest, right? Yeah.
But all implies all.
Yeah. Basically, right. But he can lie. But he's lying. Right? He's lying. And he's not that guy. He's not the honest guy. He's a liar. And he said he lies that all Cretans are liars. So it's possible only some Cretans are liars, right? Including himself, right? So it's possible that a few honest Cretans, maybe 99%, right? But he himself is a liar. So I think that is solvable, right? Yeah. 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 There's no, because the least mistake, like the guy, there's negation of all Cretans are liars is all Cretans are honest. That's where paradox comes. But actually, all Cretans, right? All Cretans are honest, right? All Cretans are liars, right? Let me show this. Let me write this. Okay. I'll do one more. Yeah, new. Don't say. You see, all X. Oh, come on. Okay. All X. How do we write? Cretan. Cretan X follows liar, right? Is this actually correct? If you for all X, if Cretan means you're a liar, right? So negation of this, right? So if you want to negate this, right? Oops, again I can't spell. I can't. What's up? Oh, what is going on? Right. So I'm gonna. What's it? Okay, so if I negate this, right? I negate this, right? So for negation, it doesn't mean there are no Cretans. So this means there exists, right? There exists Cretan, right? Yeah, Cretan on who is not a liar. I'll just say, honest or not a liar, basically. Oh yeah, and that's negation here, right? The reverse. You don't have to say all X, no liars whatsoever, right?
That's actually
Yeah.
the rule how
Yes, that's yeah, exactly. So it's vice versa, basically. Okay, so yeah, so this is as I said, these paradoxes. Some of them are actually not real paradoxes, but there are some paradoxes which are basically you can't answer within the rules of first order logic, right? So what Gödel did, if you read about what he did, is he was working before computing, right? Before Turing's tape, right? He came up with his own numbering system for theorems, like for statements. So he basically made a way of creating a paradox with his numbering system of numbering statements. That basically showed that you can build in any formal system, you can build in this type of sufficiently powerful system, you can build these sort of paradoxes, which you cannot answer, basically, right? Basically, he became best friend of Einstein, of course, in the process, right? So, but yeah, of course, if you read about him, he had a sad ending to his life, right? He ended up kind of like Howard Hughes. He only ate, I think, boiled eggs during his life. He was afraid he's going to be poisoned or something, right? So there's a thin line between genius and insanity, I guess. That's the takeaway, right? So don't be too sad that you have not come up with your own incompleteness theorem, right? So recursion, can rot your brain basically, right? So okay. So what else do we need? Of course, so we mentioned that. So yeah. So the fact is that, right? So for AI, what does it mean for AI? Of course, this, right? So this means that this formal system, of course, is not going to be a general AI, right? There was a big push in the 1980s that these type of formal logic systems, based on this type of systems like Prolog, right, was supposed to solve the AI problems, but it didn't happen. So we got our last AI winter in late 80s, early 90s, right, which lasted till like about, say, 2013, 2014, right? We have different approaches, right? We'll see later on in the course whether the new approaches, right, are solving all our problems, right? Not yet, right? But I think this, so my takeaway from this actually should be that the first order logic still has a place, right? Again, you can plug in some, you have some knowledge system, right? You have maybe large language models, some good stuff, but maybe you need also a place for these first order based knowledge bases, sort of work together, basically, right? I think that's my sort of feeling, gut feeling, really. Don't ask me to prove it because we don't know, right, the future yet. But it will be useful. It's still useful already, right? So now let's see what else we have. Are we almost finished today? I think so. But yeah, go else. Completeness. Yeah. Oh yeah. One more thing is, if you have not read it, I highly suggest this book is fantastic. Anyone has read this book? Well, Control Z. Oh. Where is my? Oh, I didn't want to say it. I'm not gonna. Oh. I'm not gonna. Oops. One second. Oh yeah, I didn't want to. It's basically about recursion, about intelligence, about AI. Gödel, Escher, Bach, right? Basically, for a Pulitzer Prize, basically, it's basically actually really about computing, really. If you think about intelligence, mathematics, right? He really sort of likes recursion, right? And how order sort of emerges, right? So, it's many of these things will be sort of like, you know, kind of you study computer science, kind of not so hard, right? But basically, how you can have a system which has basically, you know, ants, right? Ants, sort of like basic unit, right? And you get some sort of meaning out of anthill might be, you know, some can be more than its parts, basically, right? So one of the themes. But it's you can read it by chapter, right? Very, very interesting book, right? Sort of like, but it's basically, of course, a lot of, you don't have to read all the chapters. It's famously hard book because lots of chapters are sort of like playful, right? There's lots of things like backward, forward, like in Tenet, right? Read backwards and forward, right? So you don't have to read all of the chapters, right? See, okay, this looks kind of interesting. Read that chapter, right? You can find out, right? So this is a pretty famous book, right? And he's still actually, I hope he's still alive. I think he is, right? Yeah, I think he's still alive, yeah. Cognitive computer scientist, right? So, but of course, like I said, he's, you know, like he was pretty revolutionary in the 1970s. Now, right, not so much maybe, I would say. But yeah, recursion and self-reference is basically the big theme. So let me see what's happened here with my, I don't want to delete this. Where did I? Oh, there it is. Okay, good. All right. Yeah. Yeah. So Frigg, right? So, oh yeah. Maybe one more thing before we finish. Yeah, before Kurt Gödel, right? Russell, who's a very famous logician, mathematician, philosopher, they wrote a huge book, right? Principia Mathematica, right? And they spent, I think, 400 pages proving it 1 + 1 is 2, right? Right? So that's how they did. And this is like, if you check this example, let me see here. Oh yeah, where is it? Oh, there's source. So there we go. Let me show you this one, right? Yeah. 3 books, like they spent, I don't know. And the thing is, they must have been so upset when, like 20 years later, Gödel says, all the work you did really, it doesn't really do anything, really. All this work proving 1 + 1 is 2, it's not really, it's not the foundation of mathematics. You can't really, you know, use this approach. I mean, you can formalize, there's some certain limits, right? So, they have funky syntax, right? I don't recommend, this is not the book I recommend, right? Right. Even if you're a desert island, this is the only book, right? I don't know, right?
If you're making mathematics,
Yeah. Yeah. Yeah, so the idea was, yeah, we could do this, and then it's sort of like automatically follows, everything follows after that, basically. Cool idea, right? But basically you can't prove everything, unfortunately, right? Yeah, yeah, yeah. Because what he did is, Russell, he knew about the paradoxes, right? And he thought he could solve paradoxes by doing what? Essentially adding static types to mathematics, basically, like type checking, basically, in programming, sort of like idea. Again, this is before computing, of course, right? That was his idea. And he thought that would be enough, but it wasn't, right? So, yeah. List of it's top 100 English language non-fiction books, yeah. But I don't know how many people have read it, right? Yeah, yeah. Yeah. Even Russell said that he was horrified. Yeah. 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 So this is basically, interesting, but yeah, fail, basically. Okay. So what do we do next? We go this on Thursday, we're going to talk about knowledge representation, right? How to diverse facts. That's next on Thursday. Thursday, unfortunately, there's some sort of accreditation meeting, so it might be another short lesson, or maybe I'll give you something to do, but nothing too hard. So not great for sure. So, okay, so let's double check. Oh, okay, we have Ortus. And maybe on Thursday I'll have a second homework ready for you guys. It's going to be some sort of game, right? You want the second homework, right? You wanted it, so, right? So yeah, for submission you have 6 hours, right? Yeah. Yeah.
You changed it to be Friday?
No, on Friday you wanted me to change to Sunday, and I had an extra day, so this Monday, right? Or do you want more time? No, you're fine, right? You're fine. One extra day? So how many people have was for 1 day extra? Oh, okay. So. Okay. All right. So I want to see some nice write-ups. Okay. No. If I see somebody submitted on Friday, they will not be more lenient, right?
No, just don't increase the expectation.
Yes. No, we'll keep raising the quality bar, right? Yeah. All right. Okay, I'll change so we can do this. All right, let me change. So 4th of February, right? Okay, that's it.